Welcome to the TLPCA presentation of Healthy Walls Equal Rainscreen and Ventilation, course number TLPCA-02, in association of AIA Best Practices. Our provider number is 502-111-291. All attendees will be reported to AIA CES by the provider within 10 business days of presentation. Certificates of completion may be obtained by request from the provider. Attendees must sign in with their name and AIA member number for the course attendance to be reported by provider. The learning objectives of today will be methods of wall construction, research and codes, components of a Rainscreen system, Rainscreen details, and then masonry cavity walls. Methods of wall construction. When talking about methods of wall construction, there are three main methods that are used today. The first being load-bearing masonry wall, the second, barrier walls, and the third, Rainscreen systems and cavity wall construction. Load-bearing masonry walls. When we think of this method of wall construction, there's a few things that come to mind. First is that they can be extremely expensive to build, thus why you don't see them being used in everyday construction practices today. Second is their sheer mass prevents the water from penetrating into the inside. So there's no weather barrier or WRB that is in play with these types of construction. It's just their sheer mass. Lastly is that when it comes to insulation, insulating these buildings can be a bit tricky and can only be done to the inside of the building. Load-bearing masonry wall systems are not used in today's typical construction, but they were in the past, such as the example shown of the castle in Cleveland, Ohio. Today's examples of projects would be ones of cinder block, such as large retails or commercial buildings. The second method of wall construction is barrier wall systems. Barrier wall systems are the most typical method used today, for the simple fact that they are easy to build and one of the more inexpensive types of construction. The issues with this method is it is set up to stop water at one layer. Also, that there is no control of moisture penetration. When a leak is present in the barrier wall system, it becomes an improperly designed Rainscreen wall system. Most barrier walls likely function in this way. When the moisture gets introduced into the wall cavity or behind the facade, there is no energy or airspace that will allow for proper drainage and ventilation. The last method of wall construction is Rainscreen systems or cavity wall construction. This type of wall construction assumes that some moisture or water will penetrate through the cladding. That penetrating water or moisture is then collected and discharged from behind the wall. Types of this construction can be in stucco or stone, lap siding, brick, or masonry. The most common forms today would be in your brick and mortar construction, where your brick is laid on a brick ledge with 1 to 2 inches of airspace behind it for that moisture to collect and then discharge, as well as add airflow and ventilation to help the drying potential of the wall system. Benefits of a Rainscreen product include the following. There is a drainage cavity to allow water to drain down the weep screed and out of the wall system, thus getting bulk water and moisture out of your wall system as quickly as possible. Second, the airflow that is introduced into the wall cavity allows moisture inside the wall to be able to dry as fast as possible. This raises your drying potential for your wall system, thus giving you the best chance to protect your walls for years to come. We all know that it takes seconds to get something wet. It can take days, weeks, even months to get something dry. So having the highest drying potential for your wall system is your best opportunity for longevity. Next, in plaster assemblies, it prevents the mortar from coming through the lath and attaching to the paper, thus creating a mortar dam. Next, it also helps transition between dissimilar veneers and materials that can be entryways for moisture and water into your wall system. I can't remember the last time a building has been built with just one type of product, whether it be brick or stone, stucco, siding. We tend to like to throw multiple veneers and facades on our projects, thus creating transition points and weak points within the construction wall for moisture to find its way in and cause problems. Last is with cavity wall construction. Just like with stucco assemblies or plaster assemblies, the products can help ensure that there's no mortar damming or mortar bridging. So when we think benefits of a Rainscreen system or a product and why we're even talking about that today, there's a few reasons why. It's really cause and effect. Whenever you talk to the old timers and the people who have been in the industry for a very long time, they will say that they have built structures that have never had any moisture problems, and they don't see why there's moisture problems going on today. They haven't changed anything, so it's not their problem. And they're correct in a way. It's really all the things we've changed in the building envelope that affect the facade that's causing these moisture problems. Back when we didn't have any air barriers, we didn't have any blown-in insulation, we didn't have any continuous insulation outside the building, we didn't have tight windows and doors. Our buildings and our structures were very leaky. They unfortunately used up a lot of energy, but with that usage of energy, it passed through that structure, leaking through the outside. That helped dry our walls and keep our walls dry. That's why we don't see as many moisture problems in the past. Now that we're getting more energy efficient and greener and making buildings tighter, it's a cause and effect. With taking away that energy movement to that wall system, you are now making it harder for our walls to get dry. Thus, without airflow, that moisture stays behind our facades, and all it has is time. And moisture and water will wait and wait and wait as long as it needs to start eating away and taking advantage of the system that it has and tearing away at our structures drop by drop. One of the best examples I have of older construction and the durability of it, as well as the usage of energy when thinking of a project like that, and then new construction and how that affects our facades and even the moisture drying potential of a building, is really, my parents bought a house that was built in 1907. They had purchased it whenever I was a young boy, and they moved it across town, and it sat there for a very long time until they were able to actually redo it and then move into it. It was 80 years, I guess, before they were actually able to, from the time that it was built to the time they were actually able to redo it and get into it. And really all they had to do was rehab the inside, redo the doors and kitchen areas and bathrooms, because it was all torn up, mainly because of kids getting into it and kind of tearing it up. It was always a haunted house of the town. But the actual outside of the building, they just had to knock off the old paint and repaint. About 6 years into living in the house, my father thought he was going to be, a smart guy and be energy efficient and go green. And he decided that he would rebuck and redo all the windows. He would blow in insulation wherever he could, thus tightening up and making our building, our home, more efficient. He got tired of paying those extremely high electric bills in the summertime whenever he would try to keep the house cold, but it was extremely difficult. Well, those first few years after he did that, he thought he was pretty smart. The energy bill was lower, he was happier, the house was cooler. Overall, it seemed like a great decision on his part. And then growing up, I thought it was. I thought, way to go, Dad. But then I noticed that he had to start repainting the house every few years because of premature paint pill. And then all of a sudden, a few years later, he was having to actually get new wood milled to change out some of the siding from moisture damage. Personally, I thought, okay, this is how a house gets used and it's worn down and it's part of owning a home. But then looking back, I realized for 80 plus years, it had never had moisture problems. There were broken windows. Rain was getting in the structure all the time. It was getting wet for 80 years in the same location, and yet there was never a problem with the wood or the siding or structurally. So what had changed all of a sudden? What had changed was the blown-in insulation, the rebucking and tightening of the windows and doors. A house that used to sound like a ghost would go through it at nighttime with a had no longer had that noise going through it, so all that energy that used to pass through those walls no longer did. And that's kind of the aha moment of how we used to build and why our walls never had issues, and then how kind of we're building, and really that's not even to the extreme of how we build nowadays. It's kind of a medium, but how that slight change can have an effect on how our homes and walls can handle moisture and the drying potential that they lose and what that does to our projects. Moisture problems. The way to control indoor mold growth is to control the moisture. USA Today, June 20th, 2002. 90% of all mold cases are related to water leaking through the exterior finishes. Builder Magazine, May 2002. These are examples that show moisture will not only deteriorate our building products and can cause problems on the outside of our building, but they can also cause problems on the indoor air quality and indoor health of our buildings from a mold standpoint. Next, we will go over some pictures that kind of show the worst case scenario when it comes to moisture damage or moisture intrusion behind our facades. If there's one thing that I've learned about the facades that we have today, is that they're very good at hiding on what's going on behind them. Whether it's natural stone, manufactured stone, siding, brick, stucco as well. These products are manufactured and made to withstand a lot of issues and problems that go on behind them before they truly show what's going on to the front of the wall system. Just like in the picture below, you will see that the stone looks relatively clean in comparison to what's going on behind it. In this project, there was a thought that there were just a few window problems, and once they started peeling away the stone, they realized quickly that they had a larger problem at hand. You can see where the stone is discolored and darkened along the base of the windows and along the doors. But through that whole wall system, just like on the project to the left of it where there's just OSB, they had to peel off all that product, peel off all that wood due to moisture intrusion behind that manufactured stone. And in this next picture, you'll see kind of a close-up, but again, the facade is hiding really what's going on behind there. They started digging into it and noticed that there wasn't just a slight moisture problem, there was a huge moisture problem. So much so that the OSBs have been rotted away and eaten away by the moisture, as well as it's working its way into the insulation. The next picture is the picture from inside of a structure where they pulled away the drywall and insulation and then noticed what was going on from the outside in a moisture problem. You can see where the moisture is starting to eat away at the OSB as well as the framing membranes, and causing structural damage. The next picture is from an outside of a structure where you can see that the OSB is literally falling apart and crumbling, and there's moisture damage all throughout, both the OSB and framing membranes. These next two pictures are from the same project, in which they thought they again had a small window leak, and as they started to tear away the facade, the area in which they saw the moisture damage kept growing and growing until they had the whole front side of this project torn off, and between the OSB and everything else, it was just getting eaten away. Some points to where there was actually no OSB was even there anymore, just like in the second picture, where it's just 2x4s and insulation once they tore off the facade. This is what's occurring behind our facades, and this is what they're hiding. Again, they hide it very well until to the point at which you notice it, and then it's too late. Then you come to this type of problem where you not only have a moisture problem, but you no longer have sheathing material or potentially even framing membranes that are complete. The last two pictures that I'm going to go over are two pictures that definitely have moisture problems, but more than likely could have been at least helped or avoided with just a little more attention to detail. The first one is of a project where the moisture that hit the roof and rained down went down the wall and soaked up in one area, almost like putting a water hose on this one portion of the wall every time it rained. The product that they missed is the kick-out flashing at the roof. With the kick-out flashing, all that rain and that moisture would have gone down, hit the kick-out flashing, and got kicked out and away from the structure, thus giving it a better chance of getting dry and not always being so wet. In the next picture, you'll see the same thing. They missed the kick-out flashing. So now the moisture is just coming down the roof, going right over the edge, and just constantly, like a water hose, wetting that facade and making sure that it stays wet behind whatever facade was used. This gives your walls no chance to get dry and will always have problems. Now, if you create air spaces in these two structures, then you have a better chance, even with these missed details, to at least once they get this wet, they at least have a better drying potential and a higher drying potential to save your structure in the long run. Researching codes, studies on the need for Rainscreen. There are many research projects out in the world today, but we'll focus on a few here for this presentation. Wind-driven rain study for the Governor's Road Project. Simulation of wind-driven rain and wetting patterns on buildings. And last, the migration of water by capillarity. In these first two studies, it's all about wind-driven rains and the effects they have on the building envelope and our facades. The main conclusion from both of these is that the more moisture that you get on your facade, the higher chance or probability you have of having a moisture problem. It's a pretty simple concept. More moisture equals more problems. One of the good things that kind of came out of this study is they realized a one-story building with an overhang of at least 1 foot has in the low teens chance of having an actual moisture problem, whereas a one-story building with no overhang has a higher chance of in the mid 80s of actually having a moisture problem. So in the last study, the migration of water by capillarity, this is the more interesting of the three. What they looked at is how actually moisture is not only staying in our buildings, but actually moving up and out through capillary action. Think of having a cup of water and placing a paper towel inside of it, and after a while, that moisture is going to move from that cup through capillary action, through the paper towel, and actually create it to get completely soaked over time. And again, this is all through capillary action. So just like in our building envelope, just like a barrier wall system, you have your sheathing material, you have your WRB, and you have your facade so tightly squeezed together that moisture is not only just staying back there, but it's actually moving up and out versus down like it should. The last research project that we'll look at is drainage and retention of water by cladding systems. This study really dove in to 3 different wall systems on how these walls drained as well as how these walls dried. So with the tested wall assemblies, there were 3 different framed walls and how they were constructed. The first wall had no airspace. It was framed up with OSB as its sheathing, a polymer-based weather barrier, and then cement board siding and wood siding attached on top of that. The second wall had furring strips, wooden 3/4 inch wood furring strips. So it was OSB sheathing, polymer-based weather barrier, 3/4 inch wood furring strips, and then cement board siding and wood siding placed upon that. And the last wall was with drainage mat. It was a 1/4 inch entangled net drainage mat. So that wall was built as an OSB sheathing, polymer-based weather barrier, the 1/4 inch drainage mat, and then wood siding and cement board siding on top of that. So in this research project, they had all 3 walls and they introduced moisture to all 3 of them. So they essentially introduced moisture and then measured how much came out of the bottom side to see which wall drained the best. In doing this, they noticed that the 1/4 inch drainage mat actually drained the most moisture out of it compared to the 3/4 inch wood furring strips and then the wall with no airspace at all. The reason for this is obviously the wood furring strips are made of wood. They absorb and release moisture, so some of that moisture was retained in that wall cavity whenever that moisture passed through it. Unlike the 1/4 inch entangled net drainage mat, where it's made of plastic that does not absorb or release any moisture. Next, they added air movement to the walls to see which wall system would dry the fastest. In doing this, they found out that the 3/4 inch wood furring strips dried actually the fastest, with the 1/4 inch drainage mat following there shortly after, and then the barrier wall system with no airspace not drying at all in enough time for this study. So what do we learn from that? Even though the 3/4 inch wood furring strips had more moisture in it, it dried faster. And that's because it was actually 3 times the airspace than the 1/4 inch drainage mat. So they perform similarly, but in the best case scenario, you want a product that is not going to absorb or release any moisture like the plastic drainage mat, and then you want the largest space available, such as a 3/4 inch wood furring strip. So something that's not going to absorb or release any moisture, a large airspace, gives you the best potential to get the bulk water out and the best drying potential possible. So the sooner that water entered behind the cladding can escape, the better the wall manages moisture. The codes portion. IBC Chapter 1 Administration 106.1.3 Exterior Wall Envelope. Construction documents for all building shall describe the exterior wall envelope in sufficient detail to determine compliance with this code. The construction documents shall provide details of the exterior wall envelope as required, including flashings, intersections at roof, eaves and parapets, means of drainage, water-resistant membrane, and details around openings. We always want to make sure that we're thinking of drainage. The most important thing we can do is get that moisture out of our walls and away from our buildings as quickly as possible. 2006 IRC Code, Exterior Covering Section 703, Exterior Plastering Section 703.6, 703.6.3 Water Resistant Barriers, Water-resistant barriers shall be installed as required in section R703.2, and where applied over wood-based sheathing shall include a water-resistant vapor-permeable barrier with a performance at least equivalent to 2 layers of grade D paper. The exception: where the water-resistant barrier that is applied over wood-based sheathing has a water resistance equal to or greater than that of 60-minute grade D paper, and is separated from the stucco by an intervening, substantially non-water absorbing layer or design drainage space. This is important to know when it comes to adding a drainage mat to your plaster system. If you use a 60-minute or greater WRB, then you can use that WRB in a drainage mat, being your design drainage space, and meet code. If your WRB does not equal 60-minute or greater, then you will need to use another layer of 10-minute paper, and then your drainage mat to meet code. The difference being that you will take 3 trips around the building if your WRB is not 60-minute or greater, thus costing you even more money. Manufactured stone. Some building codes require a Rainscreen behind cladding materials, including manufactured stone veneer. If you are installing manufactured stone brick veneer in one of these jurisdictions, or are concerned about extreme weather conditions, it is recommended that you choose a Rainscreen system that can achieve the following. Create a space with a minimum depth of 3/8 inch, 10 millimeters, and a maximum depth of 3/4 inch, 19 millimeters. Unless otherwise designed to manage moisture vapor, the system should be vapor open. And last, the materials should be corrosion and rot resistant. Next section is 2005 National Building Code of Canada, section 9.27.2.2, item 1B. Products, materials, or systems must allow drainage, create a 10 mil gap between the 2 planes of protection, and be not less than 80% open in cross section. In this picture, you will notice that it is a map of the United States broken out into categories of extreme, high, moderate, and low moisture exposure throughout the United States. And just like Joe Seabrook says, moisture management strategies are recommended in all climate regions and are essential where average rainfall exceeds 20 inches, which as you can see is most of the United States. Components of a Rainscreen system. The components that make up a Rainscreen system are as follows: the cladding types, Rainscreen products or airspace, and then weather-resistant barrier or air barrier. Some of the cladding types would be stucco, masonry, thin veneer stone, brick, or lap siding. Rainscreen products and airspace. When trying to achieve an airspace, you want to make sure that it's a minimum of 1/4 inch. This is to the reason that this is the approximate size at which a bead of water can no longer hold its own weight. Thus, you get proper drainage and then capillary break, as well as ventilation. Weather-resistant barriers. When people think about a WRB or weather-resistant barrier, they don't really think of it as a system. Typically, they just think it's a wrap or a fluid applied of some nature. But in fact, it's an actual system approach, just like a wall system. You have your drainage plane, which is your weather-resistant barrier, your air barrier. You have your flashing, which goes around windows and doors and penetrations. Then you have your drainage weeps, which go above doors and windows, above flashings, help weep and drip, get moisture out and away from your building. When looking and thinking about which WRB you're going to use, it's always best to go with that system approach. Something that is from one manufacturer so that you know they've been tested and approved to work well together once covered up whenever heat and moisture get added to it, so there's no re-emulsifying or leaching or problems of that nature. This sounds easy, and it is, but how do you provide the Rainscreen element? What to look for in an airspace or Rainscreen product? You're looking for a minimum thickness of 1/4 inch. You want to make sure that it creates an airspace that is a minimum of 80% open air, that it does not release or absorb any moisture, that it's easy to install, that it can transition between dissimilar materials, and that it's fire resistant, passing ASTM E84. Drainage mats. What are some good characteristics of drainage mats? We look for a product that comes in a roll. Most contractors are used to using rolled goods on the wall system, thus just making it easier to handle as well as easy to install. Making sure that it has an overlap fabric of 3.5 inches for the shingling effect, to ensure there's no mortar that can get in between those cracks or air spaces, thus creating a mortar dam or mortar bridge. Ensuring that you wrap the corners and do not start or finish at the corner. Making sure that metal lath can be easily installed over the drainage mat product. And then also easy to create job site details. Ensuring that the manufacturer that the product comes from has those details, or can at least be on the job site, or you can email them to get that job site detail that may be on your project. You also want to ensure that it can handle a variety of cladding. Just like in the picture in front of you, typical projects don't just use one type of facade or cladding. We use multiple, typically brick and siding, a little bit of stucco, or siding, maybe some cedar shake with some natural stone. We like to mix and match our facades, and so ensuring that a product behind it that is monolithic, that can handle that transition and having multiple claddings on top, so that you don't have to worry about changing different products and doing different things behind each different facade. Rainscreen details. Looking at the picture in front of you, you'll see that it is a manufactured stone cutaway, where it's showing the building paper being a 60-minute or greater building paper, the drainage mat or Rainscreen, the wire lath, the scratch coat, and then manufactured stone. This would be the same cutaway if it was stucco, just replacing the manufactured stone portion with your stucco layer. So the steps when installing this is the manufacturing stone detailing, typical wall insulation. Apply vapor permeable airtight membrane from base of wall sheathing to foundation. Install metal drip flashing at base of wall. Install weather barrier, 60-minute or greater. Install drainage mat. Install the metal lath. And then last, install the scratch coat and stone veneer. Wall details for lap siding or plank siding. In the cutout you see in front of you, with any siding product, you'll have the sheathing product, OSB or plywood, your WRB, then your drainage mat or Rainscreen, also could be furring strips, and then your siding. On the top detail, you want to ensure that you leave a minimum of a 1/4 inch gap, thus allowing airflow into that system. And at the bottom detail, you want to ensure that bottom area is open, thus allowing bulk water, any moisture that gets in that system to be able to get out and away from your building. Fiber cement siding study. The reason a study was done on the fiber cement board siding with a drainage mat behind it is there was a thought that the nail would actually blow through the siding, or it would cause waviness because the entangled net drainage mat couldn't actually support the pressure put on when nailing a siding up. In the first picture you can see the drainage mat on the wall. The next set of pictures is a straight line along the wall of the siding showing no waviness. The top right picture being that it's holding its 3/8 inch airspace still. The bottom left showing that the nails didn't have any blowout, any different than if it was going directly onto the wall. And the bottom right again showing no waviness in those boards. Masonry cavity walls. Cavity walls, we'll go over the history of cavity wall drainage products and testing, new trends in cavity wall construction, and the best way to drain cavity walls. The Brick Institute of America, or BIA, requirements of a cavity wall are written in every brick application and are followed stringently in commercial masonry applications. requires minimum of 1 inch width, but it recommends at least 2 inches. Main types of air spaces in brick cavity walls. Brick cavity walls with 2-inch airspace, brick cavity walls with 1 inch of airspace or less, brick cavity walls with insulation and some form of airspace. Cavity walls with 2 inches of airspace. These types of walls are a room for mortar deflection devices to work properly. The space is large enough to prevent mortar bridging, therefore mortar is allowed to fall down into the cavity and be managed by the mortar deflection device. Cavities with 1 inch of airspace or less. Most mortar is stuck above the through-wall flashing. It is suspended between the brick and the backup wall, which prevents the mortar collection device from working properly. These mortar bridges prevent drainage and airflow throughout the cavity. Just like in the picture shown, you can see where the mortar is actually sandwiched and bridging between the brick and the WRB. This can be a huge problem because it collects so much moisture and also impedes the airflow behind the brick. Brick cavities with insulation and airspace. Recent trends in building envelope science has increased the use of air barriers and insulation in brick cavity walls. The small issues and opportunities with these wall designs. Opportunity is greater energy efficiency and long-term good for the environment. Issues, the smaller airspace in the brick cavity walls and the inconsistency of the insulation in the cavity. Both many times create cavities 1 inch or less, thus creating opportunities for that mortar bridging or mortar damming to occur. Solutions to drain and ventilate brick cavity walls with 1 inch or less of airspace, with or without insulation. With 1 inch or less, using a full wall drainage product. A full wall drainage product assures a clear and free drainage airspace. Just like in the pictures shown, you can see the WRB is on the wall with a full wall drainage mat being applied. Then the brick is going up over that full wall drainage, thus ensuring no mortar damming or mortar bridging, and also protecting that weather barrier from any problems that would occur with mortar damming or mortar bridging. What to look for in a full wall drainage product in brick walls? You want to ensure that it's a minimum of a 1/4 inch in airspace, a minimum of 80% open air, does not absorb or release any moisture, and meets ASTM E84 fire rating. ATI wall drainage test study. Project summary. 5 foot wide and 10 foot tall high steel frames were constructed to support the brick test walls. A 3-ounce copper flashing was employed at the base of each wall and provided coverage 12 inches up the polycarbonate sheathing. Wall number 1 consisted of dovetailed product, utilized 3 weep vents in the top and bottom courses of brick. Wall number 2 consisted of the full wall drainage product of 1/4 inch thickness and utilized 3 weep vents in the top and bottom courses of brick. Each wall was constructed with standard modular bricks with a smooth face and type N mortar. Wall number 1, a single course of brick were laid, then the dovetailed mortar collection device was inserted into the 1 inch cavity, the full width of the wall. Wall number 2, the entire polycarbonate backup wall was covered with a full drainage product at a 1/4 inch in thickness. The test results of this project. We're going to look at the measurement of the mortar bridging, the drainage results, and the airflow results. The measurement of mortar bridging. In wall number 1, the dovetailed mortar collection device, there was a total of 365 square inches of mortar damming or mortar bridging in that 5x10 wall. In the second wall, with the 1/4 inch drainage product, there were 0 square inches of mortar damming or mortar bridging. Drainage results. The 10-minute test with 5 gallons of water was done on these 5x10 walls, with the number 1 wall with the 1 inch dovetailed mortar collection device draining out a total of 4.64 gallons. and a second wall with a full wall drainage mat draining out 4.88 gallons. The reason there's less moisture coming out of the number 1 wall is due to the fact of all those mortar dams or bridges collecting that moisture and not allowing it to drain out. Airflow results. The airflow measurements were per ASTM B283. In the first wall, with the 1-inch dovetailed mortar collection device, at 25 miles per hour, they measured 15.8 cubic feet per minute. At 50 miles per hour, there was 37.9 cubic feet per minute. On the second wall, with the full wall drainage mat at 1/4 of an inch, at 25 miles per hour, they measured 24.2 cubic feet per minute, and at 50 miles per hour, 51.4 cubic feet per minute. You're seeing more airflow allowed through the wall on the second wall due to the fact there's no mortar dams or bridges getting in the way, impeding that airflow. How to drain masonry cavity walls. In summary, cavity walls with 2-inch or greater airspace, it's recommended to use a mortar deflection product above the through-wall flashing, the shelf angles, the windows and doors, as well as use weep vents at the top and bottom of the walls to allow for proper airflow. Cavity walls of 1 inch or less of airspace, it's recommended to use a full wall drainage product of a minimum of 1/4 of an inch. Use everywhere there is masonry, as well as use weep vents at the top and bottom of the walls for the best ventilation possible. In summary, we create a Rainscreen wall system by ensuring airflow, allowing water drainage from behind the cladding to the exterior, and creating an airspace behind the facade. Thank you for your time today.